Earlier we saw the iterative averaging example, which is a very simple representative of common science applications. And here's the code schema that we went through. You have an outer sequential loop that goes through a number of steps, and an inner parallel loop which can be grouped with iteration groups. So you have a for all g and then a sequential loop for each group. And we talked about the fact that the number of tasks created over here is n steps times the number of groups. Now we can reduce the number of groups to the number of available processors, but the number of steps is a property of the underlying mathematics. Even for the simple iterative averaging, it can take hundreds or thousands of iterations to converge to the kind of solution I showed you earlier with 0, 0.1, 0.2, and so on. So how can we do better? And this is exactly where for all loops with barriers can help. What we would like to do is create a for all loop with one iteration per group. So that's the scope of the for all. And within the for all, we would like to have the sequential iterative loop. So we've kind of pushed that iterative loop inside. And then within the iterative loop, we'll do the work for the group. That's exactly as before. So my group and so on. And we will update new x sub I as before. But here's the interesting thing. Before we move to the next iteration, we have to make sure that all the elements of new x have been completed. So we have to make sure that each task for every group has completed its work for one step before moving to the next step. And that's exactly where barriers can help. So the next statement acts as the barrier. We will also need to, as before, swap the old x and the new x pointers. And then we can go to the next iteration. So what we have is, as opposed to the earlier version where we had n steps times ng tasks, what we now have is that we only have tasks ranging from 0 to ng minus 1. Each of them does the work for phase 0, phase 1, and so on. And the barrier ensures that each task completes its work for the previous phase or step before moving to the next phase. So with this, the number of tasks that we have is just ng. And we could reduce this to just the number of processors, and we don't have the additional overhead of the fact of n steps as we saw over here. So now we've seen for a very important class of applications that are exemplified by the simple iterative averaging example, we can use for all loops to exploit parallelism. And by using this coding pattern of having the for all outside and the for inside with the barrier, we can reduce the number of tasks to just the number of groups that we have, thereby creating very efficient parallel solvers for these real world problems.